let me introduce you to the works of a guy called Martin Salfitti. A really great designer and a pleasure to work with. And when we met, we've been discussing this work here. So it's about these weird and wonderful, squiggly, squishy organic shapes. And he built them in Houdini, I think 16.5 or 17, still using grains. And we've been discussing how I'd actually approach them when I'd use vellum. And it took me a few attempts to actually figure out a quick setup that also computes decently fast. So here's how I would build those creatures. Let's start out using a sphere. Dive in there and onto the sphere. Let's make it a polygonal mesh with like 6 or 7 subdivisions. And then scatter a few points onto that sphere. We're just building out our initial shape here. So maybe like, say 20 points. And use a copy to points, copying those spheres onto those scattered points like so. And maybe in here, dropping down an attrib randomize to randomize our p-scale value, which has only 1 dimension. And let's say it should go from 0.1 to 1. And maybe let's make those spheres a bit smaller, like so, and merge those with the initial sphere here. So this is my initial shape, which I want to turn into those gooey creatures now, or into a gooey creature, more precisely. So I'm gonna use the points from volume, maybe dial down the volume separation and set the point configuration to be tetrahedral, which leaves me with 90,000 points, maybe. For now, for experimental purposes and for testing purposes, let's just dial up the point separation again, so we'll end up with quite a bit fewer points, so about 11,000. All right, next let's drop down a vellum grain. So we want to configure this as a grain here, like so. And we could immediately drop down a vellum solver, attach this, and when highlighting it, increasing our substeps to 5, decreasing the constraint iterations to 10, standard settings for my grain interactions, and also let's dial in a ground plane, which should sit at maybe minus 1.6, like this. And let's just, for a first try, simulate this. And of course, this very much behaves like a bunch of grains, individual grains that are not sticking together by any means. So let's fix that by dragging down that vellum solver and in here, wiring in a vellum glue constraint. And to show you what's going on here, let's drop down a null, wire this to our constraints slot here and highlight the null. So we are going to use the vellum glue here to build a constraint network that keeps those individual grains, those individual points attached to each other. We do that by setting the geometry type to points and the target group to points as well, resulting in those initial connections. However, not all points are connected here, and those connections are rather sparse. So when we scroll down here in the glue constraint, what I want to do is increase the constraints per point to, let's say, 8 or 9, and I can dial back the maximum number of search points to the same value as my constraints per points value. Let's again hit our vellum solver and resimulate this. And now that's a bit better, although I'm getting these fractured fragments here on the sides. So let's reset that and dial in our vellum glue again by highlighting our null here, zooming in a bit, and maybe increasing our maximum number of search points and the constraints per point to say 12. Again, highlighting the vellum solver and resimulating this. And again, we need to tweak those values. So that's what I actually do and edit out in the videos when I talk about those magic numbers that I came up with for a given setup. So I will just fast forward to this process. Yeah, and that seems to work nicely. So I ended up setting my maximum number of search points and constraints per point to 12, while increasing my maximum search distance to 0.2 to reliably find adjacent points and connect them to each other. Now, what can we do with this? So at frame 60, my simulation has kind of settled here. I'm having this blob lying there on my ground plane. So maybe let's, instead of leaving it resting there, animate the strength of the glue constraints, which currently is not very strong. The stiffness is only set to 10. So enable to animate those, let's create an output group there called stretch. And within our vellum solver, let's drop down a vellum constraint property, wire this in our false output, and up here, check the group checkbox and select only the, reset this, the stretch group here. Let's just quickly disable the automatic update, set it to manually. So what I'll do is I'll maybe go to frame 59, check my stiffness, which has been set to 10. So nothing should change with that. I'll keyframe it and go to frame 72. And here I'll set my stiffness value to say 300. So those constraints should be a bit stiffer. Let's reset this, go up one level and re-enable our auto update and resimulate this. So now we've got this slimy ball, slimy creature just moving up by strengthening its muscles, so to speak. Let's dial this in a bit. Again, I'm going to disable auto update. Go into my Vellum solver and shift click on the tab here to open up my animation editor. Press H to bring in my keyframes here and maybe move them a bit to the front. Let's say to frame 48 as a start frame, and let's put the end frame to frame 60, and maybe at frame 84 set another keyframe by alt clicking in here, and then go to 96, where I'll set my stiffness back to, say, 7 in this case. Let's go up again, reset this, and rerun the simulation before we have to enable the auto update. So we end up with this funny looking blob here. Let's check real-time toggle and watch this one more time. Yeah, I really like that. So the final question for this setup, and there's really nothing more to it, is how would you animate a mesh with this? So let's reset this and save this before we do anything else. Okay, so how would you animate a mesh? Well, let's first create our mesh, and we basically want to use this, our initial geometry, as our mesh. So what you could either do is just use this geometry straight, or maybe use a boolean to fuse those together using a union. But let's try it first without the boolean and see how that turns out. And all I want to use here is a point deform. Point deform takes the mesh we want to deform and the initial point configuration. So the initial point configuration before we start our simulation is this, our grains here, which does not move even through the simulation. And then the deformed point position, which is basically the output of our simulation. So this one here. And fingers crossed, that's all we needed to do. Let's see how that looks. Well, there are some issues here and there. So let's reset this. And again, I might fast forward through the sequence. Yeah, and in this case, it was just a matter of simply increasing the capture radius a tiny bit from 0.1 like this, which yields those jaggy results, to 0.2, which gives us these smooth results here. Again, you could put this initial geometry here into a boolean to remove those inner parts of the geometry if you'd like to, but as far as I'm concerned, that's working decently. So let's have a look at it again. So yeah, this is Martin's blob creature, now also working in Vellum and not only in the standard grains. Again, hope you had fun in this quick tip. If you get the chance to work with Martin, say hi from us at Entagma. After all, he's just a great guy. And until next time, it's cheers and goodbye.